self-driving cars and the taxi service. I think this is, despite setbacks, this is one of I think the most promising uses, in my opinion, of technology that impacting the real world. And very happy that Cohen has agreed to speak to us.
Sure. Just maybe need some help.
Yeah.
So, or not to be funny, but is your parking okay for today? Because I have these parking passes.
Oh, good.
But I don't want them to pay for parking.
Right. So then, I'll give you a brief overview of what data scientists do at Cruise. It's pretty different than everything you heard today. And I'll try to dive a little deeper into some of the problems that my team at Cruise is working on, which are related to vehicle routing that we just heard about. And again, data scientists like me, we don't work on the more autonomy side that you hear about. Like, these are mostly machine learning engineers. But data scientists still do a lot of important things at Cruise. So there are two areas of data science at Cruise, which are like, one is like autonomy, that data scientists that are helping the autonomy teams that are developing this software on the car, measure metrics and so on. And there's the other side, which I'll talk more about, is commercial data science. So once you have these cars, these Robotaxi on the road, how do you create, a commercial service out of them? So autonomy, in the areas of data science that we help, the autonomy teams a lot in measuring safety and reliability. So, our cars drive around in the city, but they don't have a lot of accidents happening. And so we need to create this kind of like dense metrics that compute basically based on some like near accidents, compute how safe and reliable our car is, and do it with very limited driving. So we have a version of our software. We test it for a few weeks with this kind of supervised fleet of cars, and we need to decide whether this new version is safe enough to release to the road with driverless cars without any supervision. And so data science help with that. Also creating this kind of safety human benchmark. So we have accident data about humans. So we want to prove that we are safer than humans. So data scientists help creating this kind of benchmark in every city. What's the average rate of accidents for humans? And also in simulation testing. So we have a lot of investment done on simulation. And so data scientists help in creating this kind of important sampling technique, curating test cases for the source simulation. So every software version we're releasing, we want to test them in the simulator. We need to pick the right scenarios that are more risky in order to know that we are better. And then use that to understand what's our overall safety level before, again, we release a version of the software to the road. So these are autonomy team, data science. These are supporting autonomy team. And my team supports the commercial side. So once we have this kind of like nice app, there are many areas where data science is helping make it better and create a commercial product that is viable. So there are many challenges that on the data science side we face. A lot of them are pretty typical challenges that Uber and Lyft and other ride-hail companies around the world face, like how you match a ride with a request, how you route vehicles, how do you predict ETAs, how you price. These are pretty similar. But then we have these kind of like new challenges that come from the fact that we are actually controlling these vehicles 24/7, what they do on the road, what they do inside facilities. And when they get stuck, there's no human driver that can get them out of tricky situations. So that creates a lot of challenges for us, and also a lot of interesting algorithmic problems. And I want to now dive a little bit into a few problems that we're facing and how we are right now approaching them. But definitely there's still a lot of work to be done in these areas. So let's start with like going into positioning. So positioning, typically, this means how do we position our vehicles before we get a ride. So we want to make sure that once we put the vehicles on the road, we want to make sure that they are going to be positioned where we expect to have rides occurring. And so Typically at Uber and Lyft, what you would do instead of positioning, you're creating this kind of like driver incentive. You create incentives for the vehicles, for the drivers to go to high demand zones. Here at Cruise, we have higher control, and the algorithmic problem is actually very different. And so there are many works in the academia you can find about how to do vehicle positioning. Here I'm showing just one solution that we're taking, and there are still challenges, and I'm going to talk about the remaining challenges. But one solution that can be done is basically to describe this kind of like divide the city into this kind of zone. Here we have San Francisco divided into 3 zones. And then we basically define this kind of a graph where every point here represents a zone, and this is time. And so we discretize time as well. And then we define this kind of, we define how many vehicles are here at time 0. And we want to solve for the rates of transition between every zone and every moment in time. And we add on top of that this kind of like edges where these are customer trips. So if we have a trip here when we expect to have demand, and this demand basically can take one vehicle up to some different zone. It could be actually a different zone. It actually should be a different zone, and at a different time. And so this basically you can take this problem, put in your demand, put in all your zones, and you can solve it using a linear program to get these rates of transition. The rates of transition at time equals 0 basically tell you whether you need to move vehicles from zone 1 to zone 2 or other zones. So this is pretty simple, but there's like a more interesting challenge of how you combine this problem along with the matching. So matching, I'm going to match a vehicle with ride at this time, but sometimes it makes sense to take into account positioning. So let's say I have a request right in the border. Do I match it with a vehicle from here or from here if they have very similar ETAs? And if I know that I need more vehicle idling here than here, then I want to match to this zone. So you can get extra efficiency by combining the matching problem and the positioning problem. And this is something we're still in the works. But if you look, you can find different solutions. A reinforcement learning solution is also a possibility. And so a different interesting problem is how to deal with charging and maintenance. So we're positioning the vehicles, but then we need to decide when do we want to send vehicles to charge or to get them maintained, and when do you want to deploy them to the street. And here again, we want to make sure that we have all the vehicles available when we have the peak demand, and we don't want to waste our charge, basically our electricity, when we have no demand. So again, this is a work we did with an intern from Stanford last year. But basically, you can do a similar thing that what we said I proposed previously. You have this kind of like zones, and you have time. So you discretize time, and you have discretizing space. You add to this also this kind of like facilities where we are charging our vehicles. And you also discretize charge levels. And you can then put everything and optimize everything using, again, a linear program to get this kind of like optimal deployment schedule where you want to deploy your vehicles. And you can try to follow that using the real-time system. So there's a lot of remaining challenges of how to basically compute this schedule and update it in real time as the condition on the roads change. But this is the basic solution that for now, we've prototyped along with the intern. So this is interesting. This is a very different problem than what traditionally at Uber and Lyft people are dealing with, and there's still challenges remaining there. Other areas that are somewhat different is, for instance, that you don't think so much about is choosing a pickup and drop-off point. So our AVs can't really stop everywhere right now. There's a lot of places where it's not really safe, and human drivers are able to stop and block someone's garage. We can't do that. And so we need to be safe, we need to be legal, and there are other considerations that take into account. So optimizing where we're going to stop and pick you up is really important for us, much more than for traditional ride-hail companies. And so we want to take into account multiple considerations when determining that, and would be the walking time, of course, but also there's a trip time, so how long it would take to get you to your home, and how long would you have to wait. So choosing different spots may mean that there's like different driving time from your AV to your spot. And there's the probability that actually we won't be able to stop at this spot, and then we'll choose a different one. And there's also, how much we'll be impeding traffic. You want to make sure that we choose a spot where we're impeding less traffic, creating less of an issues for other drivers. And so taking all of this into account is, a challenging problem, and more or less how to balance this kind of like user, people don't like to walk a lot, but then other considerations is also an interesting and challenging problem. And so that's a relatively simple optimization problem. And we talked about vehicle routing. Of course, we, like Uber and Lyft, like a lot of other companies, we're doing, we're computing, the basic routing problems. Here, I think risk-based routing is a little different than traditional ride-hail companies. We have a much better understanding of risk because we want to understand how safe our autonomous vehicles are. And so we really know how safe is every road for our vehicles, and we know how often they get stuck in different areas, or how often they need assistance. And we also have real-time information coming in about emergency vehicles where they are stopped and other situations that are evolving on the road. And so there's a lot of challenges in how to take that into account in our routing costs and into account in routing. So let's say I want to get to this house and I know there's an emergency scene here. I'd rather take a slightly longer path, but that doesn't cross that, because then we know that the vehicle will get stuck. So taking into account a lot of these kind of risk consideration in routing is also an interesting and challenging problem. And how to balance those with trip time and other costs on the graph is interesting, and we're still dealing and solving these problems. And indeed, like taking into account a lot of interesting information about risk. So that's it. I just want to give you a few nuggets about problems that we're dealing with, and I'm happy to take any questions as I can answer. Yeah.
Yeah, so I think the first two problems you mentioned around optimal placement of, and then the charging problem, aren't those interlinked? So do you land up solving them? Because moving cars will also kind of arguably reduce the charging. So do you land up solving them concurrently, or how do you go about?
What do you mean? Explain. Okay.
So the first problem, which is optimally placed, sorry.
Yeah.
I think the first problem where you optimally place the cars, right? By moving them around, you'll also actually discharge, right? So
Yes.
there'd be usage. And then the second problem, we're optimizing for utilization.
Yeah.
So I think, just curious, aren't those two coupled? And if yes, how do you solve them concurrently?
They're coupled, yeah. So it's a good question. So basically, typically, this problem we solve with a 24-hour horizon, and it has its own objective function. And this problem you solve with like an hour horizon, it has a different objective function. And so how do you tie them together? That's a very interesting question. In principle, you can think about first problem decides how many vehicle we are going to basically get back to the facility or deploy at a fairly coarse time scale. But then the second problem also has the ability to tell, like the first problem, oh, sorry, I have a lot of demand here. I'm canceling one of your, a few of your summoning right now, and I'm not doing that. And then I'm deciding to do this, and deciding to do these kind of assignment to zones. And then there's a third, problem, which is what we do right now with like existing requests. So there are actually 3 tiers of problems here, and each of them can, has some costs of undoing what the other one decided to do. Yeah.
Thanks.
Yeah.
So the last problem you talked about, how is it different from stochastic shortest path problem?
It is not stochastic. We don't have, but no, we're not doing stochastic. It's all shortest path. So it's just shortest path. The question is, how do we set the weights correctly?
But stochastic shortest path problem is where for each road segment, we have a distribution of delays, and you want to find, say, when can I leave so that with 95% probability I'll make my flight.
Yeah,
it looks very similar because your risk is really a stochastic variable on delay.
Yeah, but for now, I mean, we could solve it, but as far as I know, it will be too slow. We have latency constraints that basically means that we need to solve the regular shortest path. Unless you tell me you can solve it in like 5 milliseconds, I'll be.
No, the stochastic shortest path is a hard problem.
Yes.
This is fascinating, by the way.
Yeah.
My question is more on the infrastructure side. So how are you collecting the data that is being produced? And are you actually collecting data from individual cars and kind of conforming them together, joining them? How does that work? Can you talk a little bit?
Depends on which data you're asking.
So all the measurements, all the optimizations you're doing, let's say you have a 1 hour horizon where you have to make certain decisions.
Yeah.
You have certain states that I'm assuming you have certain simulators that you're using, but you also have the current state that you're collecting from your cars.
Yes.
Now, are you streaming that data? Are you actually putting it on the vehicle and then somehow that gets across multiple vehicles in a given region? And how does that work?
So vehicles basically stream data back. We need to be mindful of like how much data, but yeah, they stream a lot of data back to the cloud, and there we aggregate that and then solve this problem and then send them back. It's kind of like orders: go there, pick up this one, do that. But these kind of computations are not done on the car. The car is just busy, navigating itself through the road, doing all the perception and planning. But yeah, and what it gets from the cloud is just an order: go from point A to point B. It can navigate by itself, even if our cloud is down, the car can continue driving by itself to the destination.
Okay, one more question, and I guess then.
Maybe a very simple question is so when does it take into account of the general traffic besides your autonomous cars?
Take into account in what?
Next other cars.
In what?
In your consideration of say the
routing?
timing, in navigation.
In navigation, so it depends. The navigation, from citywide, no, it doesn't take into account other, vehicles around. But when the car needs to make the decision about do I lane change right now and for the next 100 meters, it takes into account, of course, the other cars around. Yes. But,
All right. One more question.
All right, thanks. So right now you showed different optimization problems for the specific model of an Uber ride-sharing business model. So what if the business model changes? Do you consider other business models if it's, let's say, a car rental or some other business model that I haven't thought about?
Cruise is also working on a delivery product, and that's definitely different. But delivery is, very similar to this. Like a customer trip is just, it's a trip that doesn't have a human inside, just food. But for others, business model probably will need a very different system, very different backend system.
All right. Let's thank Or once more.